Important class of function called multiplicative function, and when the GCD of two numbers is equal to 1, then the function satisfies this product. Then it is called multiplicative, and it's extremely important because this enables us to do F investigation at only prime powers. Once a function is multiplicative, then you don't have to worry about all possible divisors. Only prime power is the one you should concern, because once you extract prime power, then other things are not related to this one, because we extract prime power, such as, for instance, 3 to the power of 5. That is extracted, then others can be just multiplied later. What does this mean? It means we can prove everything for just this case, and then after proving this, we can claim that it is true for the whole set of integers. So this is a strategy, and because of this strategy, this group is extremely important. Extremely important. If you don't understand why it's important, ask me. Function is called multiplicative when the GCD of two numbers is equal to 1. Then the function can be just divided into 2. Then what about this expression? I mentioned about this expression before. The sum of all divisors, we collect, right? For the sum of all divisors, we collect. We collect the function fd for all divisors. So this is the sum function of function. And last time I mentioned this. If individual addend is multiplicative, I will use MULT, then the whole thing is multiplicative. So this is the statement I will prove. So once we know a function is multiplicative, then the sum over the divisors is also multiplicative. Any questions? Then let's do it. And in fact, the other direction is true. The sum of function over the divisors is multiplicative. Then this individual function f is also multiplicative. This direction will be investigated later. So let's prove this case. Assume that a function is multiplicative, and then we consider the sum, and then we sum, and then we have mn divided by d, where GCD of mn is 1. So GCD is 1, and then we find all divisors of mn, and then find it. Then, because GCD of mn is 1, the divisors dividing the first one, and then the divisor dividing the second one, could not intersect. In other words, assume that we call this ij. Then GCD of di and dj should be equal to what? 1, because mn has GCD equal to 1. In other words, if d1 divides m, dj divides n, then they cannot have the common factor. If they have the common factor, then the GCD of m and n would have a common factor greater than 1. Do you get it? So it's impossible. Because of this reason, we can rewrite this sum using 2 divisors. Instead of using ij, just call it 1 and 2, right? It's inconvenient. Or m and n. Because we used m and n here, let's call this m, and n, right? Because it divides m, it divides n. So dm divides m, dn divides n. Do you get it or not? If you don't get this idea, ask me. And then dmn, right? So divisor also splits because of the GCD condition given by the problem, and then we decompose. Now we use the property, because f is multiplicative. Because f is multiplicative, what can you say about this integrand? We can use what? F of dm and then f of dn. Why? Because GCD is 1, right? Because GCD is 1 and the function is multiplicative, we can decompose. And then we can even decompose the sum. dm divides m and then dn divides n. Take a look, and then if you don't follow, ask me. If you cannot follow, ask me. Then now we can split it into two parts, because this has fdm and then it doesn't have dn. We can switch these two things and then get this thing. So as you can see, sum is also multiplicative, right? When two functions are multiplicative, then the sum is also multiplicative. We can split the sum into two separate parts, handling m and n. Do you get it? So when you have a multiplicative function, and then we want to handle sum, then we can just decompose for m and n, right? For m sum and then n sum. This is the key. You will see the importance of the key in the following proof. Unless you have a question, I will continue. So let's use this fact in the next example. I want to show that the function that I mentioned, the tau function or sigma 0 function of n, right? So sigma tau of n function defined by divisor, number of divisors dividing n, right? Number of divisors dividing n. This is the tau function. Then first of all, function f of n equals 1, identically 1, is multiplicative. Why? Take a look. F of mn equals 1 because of this fact. And then 1 is equal to 1 times 1. And then 1 is f of m, and then f of n. So it is multiplicative. Any questions? And the second part, sigma of n, which is defined by the sum of all divisors. Last time I mentioned these things for any power. This is zeroth power, and then this is first power, right? This is zeroth power. This is the first power. Then call the function f of d equal to d. Then this is multiplicative. Why? What is f of mn? F of mn equals what? Mn, right? Because d is replaced by mn and mn. And then m is f of m. And then n is f of n. And as you can see, the function is multiplicative, right? So, because these are multiplicative, this function is also multiplicative, right? So, we can do this, the same proof for any s power. So assume that you are asked to prove that this function is multiplicative. All you need to show is what? Showing that this is multiplicative function. And then use the refer the fact, right? Refer the fact that in addends are multiplicative, then Right? Sum ends are multiplicative, then this is multiplicative. The sum is multiplicative. So we covered this. So this is extremely important in this chapter because, as I mentioned before, once a function is multiplicative, all you need to worry is just p to the power of alpha. Why? Because if you decompose the number into prime powers, then the different prime powers have no relation. Just consider this prime power and get the result, and then use the result. Do you get it? So let's write down this thing. What divides p to the power of alpha? 1 divides it, right? P to the power of 1 divides it. P to the power of 2 divides it. Oh, sorry. I will write it clearly. Divisor dividing p to the alpha, and then d to the power of s, right? This s is attached. Then, as I mentioned before, 1 divides it, right? And then p to the power of 1 divides it, right? Divides it. And then p to the power of 2 divides it. And all the way up to p to the power of alpha. So this is it, right? This is it. So once you find out this sum, once you find the expression of this sum, you just multiply these things for individual factors. That's it. Do you get it? So assume that you are asked to find the formula. Then you find the formula for this p to the power of alpha. And then generalize it for general n. So I will write down the expression. And as you can see, 1 plus p to the power of s, p to the power of 2s, p to the power of alpha s. Then, if we add these things, then p to the power of alpha plus 1s minus 1, p to the power of s minus 1 is the sum, right? So geometric sum can be calculated. Then with this, I can write down the formula for sigma sub s. If you have a question, stop me. If you don't, then I will go to the next column. So let's do it. Find the formula for the sigma sub s when n is decomposed into P1, R1, P2, R2. Just a moment. People use K, so I will use K. K1, K2, and then PR, KR. Right? Assume that n is decomposed into this portion, this pattern with distinct PIs. We have different PIs then. Sigma sub n of n is nothing but sigma sub s P1, K1 multiplied by sigma sub s P2, K2 all the way up to sigma sub s PR, KR by the property that the function is what? Function is multiplicative, right? Because the function is multiplicative, we don't have to worry about complex divisors, just prime divisors we focus. And then we extract something. We already extracted the formula for this portion, and it says P1 to the power of s minus 1, P1 to the power of K1 plus 1 s minus 1, right? For the first part. And then you can just copy these things up to PR s minus 1, PR KR plus 1 s minus 1. So we solve this for any s. S could be 0, s could be 1, s could be 2, and so on. Assume that s is 0. S is 0, then what do you get? Strange. S is 0, then the denominator is 0. So if S is 0, then so I will write the formula for greater than 0. If S happens to be 0, then I should return back to the prime power case, p to the power of alpha case, right? I will derive the formula for this one and then use this one to find the general result, right? So this is true for S greater than 0, because S is equal to 0, and you have 0 denominator. So let's return back. Then what divides P alpha? 1 divides P alpha, right? P divides P alpha. P squared divides P alpha, all the way up to P alpha, right? How many numbers can you find? From this to this, how many numbers can you find? 1, alpha plus 1, right? Alpha plus 1. Because of this reason, we can write down sigma sub 0, or tau of n, or sigma sub 0n equal to k1 plus 1, k2 plus 1, multiplied all the way up to kr plus 1. So all of these come from very, very important fact that the function is multiplicative, right? If the function is multiplicative, you don't have to worry about very complex structure of divisors. Focus on prime divisors, and as you can see, prime divisors are very straightforward. 1 divides prime power, p divides, only p something divides. If we add, for instance, if p is not 2, if we multiply 2, p can divide p alpha? Impossible. 2 cannot divide p. So nothing can be multiplied in this series, because in this sequence, right? In this sequence. Only p should be multiplied, 1 or p. So this is it for the property, and you will see these things over and over again until the next chapter, not just in this chapter, until the next chapter, and then I will mention about a few other things. And the other thing is very important function called it's German name, so it should be read Möbius, but sometimes we ignore, so Mobius function is okay. It is mu function, Mobius mu function of n is equal to 1 if n is equal to 1. And then 0 if any square divides the number. Otherwise, minus 1 to the power of the number of divisors, number of primes dividing, number of distinct primes dividing the number. So to clarify the definition, I will give you an example. What is mu of 1? By definition, mu of 1 is what? 1. What is mu of 2? The distinct prime creating this number is just 1 number. So minus 1. What is mu of 3? The distinct number of prime dividing this is just 1 prime. So minus 1 to the power of 1, right? Then it's negative 1. Mu of 4. 4 is 2 squared, right? 2 squares divide n, so 0. If you don't follow me, ask me. Then please, as an exercise problem, in addition, I don't have enough space, please find this up to 10. Please find these things up to 10 to check whether you understand the definition or not. Of course, I will write down the result. If your answer is different from mine, tell me. I will explain. So this is called the Mobius function. And this function is very important in theory. Yes? 8 means 2 squared divides n, then 0.
So we ignore the negative 1 times, or 2 times 2 times 2. Factor out the perfect square first.
That's right. Anytime, in other words, only way is distinct prime. Only way is. If there is anything, then any repetition of any number, like 9 or 8 or 4 or 12 or 24, 0. Yes?
Why mu of A is 0?
Because 2 squared divides n. 2 squared divides 8, right? So any square, if any number square divides it, then it's 0. Like, for instance, 100, then it is divided by 2 squared, so it is 0. Yes?
Why is mu 6?
Because 2 times 3, then how many distinct primes? 2 and 3. Then there are 2 distinct primes. For instance, 2 times 3 times 5, then it is 30, right? What is mu of 30? Negative 1, right? Mu of 30 is negative 1 because it has 3 distinct primes dividing it, right? 3 distinct primes. Then I will continue. Question? No. And this function has a very nice property. Function itself is strange, but the property is extremely important. So I will divide this thing and then add. In other words, we sum this function, right? We sum this function over the divisor, but especially when we have 1. Then by definition, one number divides 1. What integer? One positive number divides 1. It is only 1, right? So mu of 1. What is mu of 1 by definition? 1. So this is it. But now, assume that we are using the number greater than 1. In other words, n here, here is greater than 1. Then what will happen? N here is greater than 1. And what will happen? Before showing anything about this, I will prove that function mu is what? Multiplicative. In other words, from this point on, to prove some difficult thing, we prove that the summand is multiplicative. This is the strategy. If the summand is multiplicative, automatically the sum is multiplicative. Then we only need to care about prime numbers. Do you get it? This is the strategy. So I will prove that this is multiplicative. So assume that. So I will write it. This is my claim. Why? Because once I prove this claim, I don't have to worry about general n. I only have to worry about what? Prime power, right? Prime power. Do you get it? General n is very complex, right? The divisor structure is very complex. But we only care about prime once this is proved. So let's do it. If GCD of m and n is 1, and m is not divided by any square, and then n is not divided by any square. Assume that m times n is divided by some square. Then what happens? By definition, it is what? 0. So it's trivial, right? 0 is equal to 0 times 0, so it's trivial. So we don't even have to worry. Do you get it? So this is the tough case. If nothing, no square divides n, no square. This is called square free in short, right? So in short, people call this kind of number square free. If m and n are square free, then m can be written by some product of distinct primes, right? And then n can be written by some product of distinct primes. Do you get it? Will there be any chance that some prime here and some prime are equal? Will there be any chance? Impossible. If there is some prime here and some prime here equal, then GCD cannot be 1. Do you get it? So, because of this reason, M and N is P1 up to PR, and then Q1 up to QS, and then there is no chance that we have any square because they are distinct group. So, mu of M and N equals mu of this whole set of numbers, right? Then, how many distinct primes? R primes, and then SR plus S distinct primes, right? And then we can multiply -1 R times, and then multiply -1 S times, right? This is the power in this exponent, right? And then -R is nothing but mu of what? P1 up to PR. And then this is mu of Q1 up to QS. And because of this reason, this is mu of N, mu of M, mu of N. And I showed that the function, especially the cement, is multiplicative. Mu is multiplicative. Then now, we can derive a formula for the top one very easy. Unless you stop me, I will continue. Then let's derive the formula for the prime power, right? Because of this reason, we don't have to worry about N. We only worry about P to the power of alpha. Huge advantage, right? It's a huge advantage. If we need to care about all possible divisors of N, then it's almost unhandleable, right? But if we only care about P to the power of alpha, prime power is trivial. So let's see the effect. Sum of mu dividing N, mu of D dividing N, mu of D was the question, because sum and mu is multiplicative. This whole sum is multiplicative. Because of this reason, we don't have to worry about this N anymore. We only worry about P to the power of alpha, right? Do you get it? You should know why I removed N and consider just P to the power of alpha. This is good enough to handle the problem. Then it is, by definition, divisor of P to the power of alpha. What divides P to the power of alpha? 1 divides it, P divides it, P squared divides it, P cubed, and then up to P to the power of alpha divides it. All these are 0 because P squared divides all these things, right? So all of these are gone. Then what is the first number? 1. What is the second number? -1. 0. This is it. This is it. So it is 0. In other words, because of this reason, now we can generalize. If N is greater than 1, then the sum of mu of D is 0. Why? Proof is up there. You didn't prove for general N. Because it's multiplicative, P to the power of alpha is enough. Yes?
Why I squared is 0?
By definition, if something squared divides it, yeah, we don't have that column, right? If something squared is there, then it is automatically 0. In other words, if we decompose, there cannot be any squared. Any other questions? In other words, in the future on the exam, for instance, I will ask this thing. Oh, what if I only asked this thing? Oh, this proved that for n equal to 1 billion, mu of D dividing this n is 0. So assume that I ask this thing. Then some people may try to find all divisors. 1 divides it, 2 divides it, 5 divides it, 10 divides it, 20 divides it. Will it work? And then write down, and then, in fact, in the past, when I asked this kind of problem, some students really wrote down these things and then said, oh, if you continue, you can find the answer. And then say, oh, because of something, it will become 0. You see the proof? No, I cannot accept it. He wasted his time, right? I wasted my time reading it. In any case, I proved this thing using the fact that the function is multiplicative, and by this fact for not general, complex n, but complex doesn't mean complex number, general complicated n, but p to the power of alpha. If you did prove it for p to the alpha, then that's good enough. So in the future, when you are handling some function in these chapters or some following chapter, then you can consider just p to the power of alpha. When you read it, regard it as p to the power of alpha. Not because it's the case, but because of the property that the multiplicative function decomposes the factors. So this is it. And now assume that you have this thing, right? Now f of n or f of d is collected to create the sum, right? This is a sum. And then I will give a name. Oh, let's give a name. Because lowercase f is used, I will use uppercase n, right? So lowercase and uppercase, I did 2 different things in this case. Then now I will use f of d here. And then I want to get f of n here. In other words, I want to switch them. Will it be even possible? In other words, from summand, we got the sum. Can you get the summand from the sum itself? Pretty challenging question, huh? And the answer is yes. Answer is yes. How is it possible? We get the result by attaching this mu function of n over d. This Mobius function of n over d multiplied together will give us this thing. So from the function we can get the sum, or from the summand we can get the sum, but we can get the reverse. From the sum we can get the summand. That is called Mobius inversion formula. So we can get the sum from summand, and the reverse is possible. If sum is given, we can get the sum. And I will prove this thing. So as you can see, in the past, we proved something that sounds very obvious. But about this point, it is not that obvious, right? So let's do it. D divides n, and then Mobius function of n over d, and then f of d is the case. So I will show that this will result in lowercase f of n. Do you get it? Then it's the proof, right? So to do it, I will write the definition of f. definition of f is something dividing, and so because d is used, I will use k. K divides d, and then f of k. Do you get it or not? By definition, f is the sum of lowercase f. Then, as you can see, we can write the sum this way. D divides n, and then k divides d, and then mu of n over d, and then f of k. All written in one big sum, right? One big sum. Then what is the technique? The technique is switching the variables. So I will call this thing. So this is the statement I will prove. If d divides n, and then k divides d, just a moment. I did not pick this well, so I will temporarily switch n and d row. For convenience, it's possible to go in this direction, but for convenience, I will switch it. So I will switch. Later, I will tell you the reason, but I will tell you the reason right now, and then I will switch these things. It's equivalent, and I will let you know right now. So I switched this thing for convenience, and reason will be explained very soon. But before then, I will write it in better form. Take a look. If D is a divisor, if D is a divisor of n, n over D is also what? A divisor, right? So it's like this. You are considering divisor of n, and n is divided by, for instance, 1, d1, d2, d3, and then eventually n is divided by n. But now reverse it. N over n over d something here, and then n over d3, n over d3, n over d2, and then n over 1. Take a look. This set is a divisor. Then n over d is also a divisor, right? Reverse order, right? Reverse order. If you multiply these, always get n. Do you get it? So if n is a divisor, then n over d is also a divisor. In other words, you sum over n over d or n over d, you will get the same result, no matter what. That's the reason I switched, so I forgot to step switching it for convenience. It's possible to follow the previous one, but it's better to follow this order. But if you don't agree with me, ask me. So I switched d and n over d in this case. Then n over d becomes d, and then n over d becomes d because I switch. If you don't agree with me, ask me. So I explained it. Then what I want to do is this thing. I will switch the role. This is the claim. If this happens, then k divides n, and then d divides n over k. This is the statement that I will use. So I will prove this thing. So I switched the role of K and D. Do you get it? Role of K and D are switched. In other words, the sum D divides N, K divides N over D will change to this thing. If you don't understand, of course, other than this part, I will prove this part very soon, but other than this part, if you have difficulty, ask me. So in the first place, I switched the role of D and N over D, right? Switched the role of D and N over D. No difference, no difference. So I did it. And then I just wrote down by definition, and then I now switched this thing, and this is the key to the proof. This is the key to the proof of this theorem. Key portion, right? So on the exam, if you are asked to solve this problem or prove this problem, then I will check whether you can switch the role. And I will explain the reason very soon, unless you have a question about the structure up to this point, about the steps up to this point. First of all, top one, I switched the role of N, role of D and N over D. No question, right, about that. And then just routine writing, right? Routine writing of the statement. And then now we arrive at the crucial point. At this kind of crucial point, you should overcome difficulties. Then let's prove this statement. I will go from this to this direction. Then the other direction is obvious. It is just almost similar as this direction. Take a look. Only change is changing D and K. So the other direction will be the same. And I will prove it from this point on. So if D divides N, in this we cannot do very many things. So I want to write it in mathematical expression. What is it? N, D divides N means N equals what? D times some number, say alpha. Do you get it? And then K divides N over D. That means N over D is equal to what? K times some number beta. What is the goal? Goal is this. Goal is what? N is equal to K multiplied by something, right? This is the goal, right? And then N over K is D times something is the goal, right? First of all, as you can see, I will divide left side and the right side, right? I will divide it, right? So this is divided, then the left side is D. If I divide, then D alpha K beta, right? Then I can multiply both sides by K beta, then K beta, and then alpha. Do you get it? Or just simple arithmetic, right? This is simple arithmetic. I divide this by this by this, then get D, and then this by this, then got D over alpha, and then alpha equals K beta. So I get this result. Because of this reason, I can achieve the first goal, right? First goal was N is equal to K something. N is equal to D alpha, because of this reason. And then D alpha, alpha equals K beta. And then K D beta. So I achieved the first goal. Do you get it? And then I will get the second expression. Second expression will be obtained very soon, unless you have a question. Let's do it. Second expression, N over K. And then as you can see, N over K is what? Alpha over beta, right? K is alpha over beta. Then it is N over alpha here, and then beta. And then as you can see, there is an easier way than this thing. Sorry for the confusion. Just use the second line. That is easier. Sorry. If we use this fact, then because of this n is equal to what? Because of this n equals k beta d, right? You get this. So n is equal to k beta d, and then divide by k, right? It's not that strange, right? Beta d. Did I prove it? I proved it. So I proved that if the left-hand side is true, the right side is true. Please do the similar thing from the right side to the left side whenever you have time. Because we don't have enough time, I will prove the other way. You may use, for instance, instead of alpha, beta, you may use, for instance, gamma, delta, right? Or epsilon, delta, anything, right? And then you can prove the other way. In other words, we add this way or add that way, but the same result we can get. Because, as I showed you, these are equivalent. Because of this reason, because of this key portion, now I can write the sum differently. So I can write the sum differently using this fact instead of this fact. Do you get it? So I can switch these two things. So I will go down and then write it. K divides n. So K divides n, and then D divides n over K, and only order of sums change it. The inner part does not change. Fk. But take a look. We can now use two sums instead of just one big sum. And then I can write this sum right here. Any questions up to this point? So we wrote a big sum, and then now we split small sums. We split it to small sums. Take a look. Here, D is required, right? Here, D is required, right? So I will handle this inner sum. If you add mu function, what is it? If you add mu function, I proved it. If you add mu function, what do you get? You may go back a few pages or a few columns to find sum of mu. Sum of mu is mostly what? 0, right? Do you get it? Sum of mu is mostly 0, but only one time it is not 0. Only one time. When is it non-zero? Right? This is 1, right? This portion is 1. When is this equal to 1? Great. So it is like this. It is mostly 0, 0, 0, but only when n equals k, in other words 1, right? Only surviving term is when n is equal to k, right? And then this result is what? 1. So n is equal to k, sum of just one term, n is equal to k. I mean k is equal to n because we are summing over k, so k is equal to n. It happens, so it is f of n. Why? Because only time this doesn't become 0 is k is equal to n, right? When k is equal to n, it's right. When k is smaller, then this automatically becomes 0, and then. So as you can see, I completely proved the Mobius inversion formula for general f. And please browse the proof. And as I mentioned before, key portion proving it is this fact. This fact. Then, unless you have a question, I will continue and then cover the next item. But if you have a question, ask me. But sometimes you want to apply this kind of theorem, so I will do the application a little bit. So just applying. I do not prove it, I just apply. This is called tau function, right? This is called tau function. Then, if you apply Mobius inversion formula, 1 equals what? 1 equals tau of n, tau of d, Mobius function of n over d when d divides n, right? Do you get it? This comes from the Mobius inversion formula. Similarly, if you add these things, then you get this n, right? Then what can you say? We can use n here, then n equals d divides n, and then mu of n over d, and then sigma of d, right? So we can write the function this way. So we can get these kind of result. And for any power, you can do the things, right? For any power, you can do these kind of things. So on the exam, if I asked you, what should be your answer? On the exam, if I asked you, write the simplest possible form of this sum. Then the left side should be a simple form, KC. What should be your answer? By analyzing the trend. So I wrote down the right column portion, and you should find the left column. So what should be the left side? Excuse me?
1.
Sigma 5 is fifth powered sum. Fifth power, sum of fifth power. What is your answer? By this analogy, you can get the result. What should be? So to give you the idea, I will give you this thing. If you don't understand, ask me. Do you get it? And can you guess this thing? You mean fifth, right? Right? And to the fifth. So on the exam, if I ask you this thing, then by Mobius inversion formula, the left side is n to the fifth. If you don't understand this trend, ask me. But if once you understand, it's not a big deal, and then we can continue. Then now, as I mentioned before, if f is multiplicative, then sum of f is multiplicative, right? Do you remember this? Right. If f is multiplicative, this is multiplicative. And then the other direction will be proved by Mobius inversion formula. By Mobius inversion formula, this is very trivial direction. It is almost identical to the one that I did with this direction. So, if GCD of m and n is equal to 1, then, and if contains all the statements, so I will save space. If this is also multiplicative, right? Not just the function here, this whole sum is multiplicative. Then Sorry, I will describe this more clearly and then continue. So to explain this thing, m times n, then m n, right? We wrote it this way, right? But to avoid confusion, I will attach subscript m here. I will attach subscript n here. Do you get it? Because to avoid confusion, if I use the same d, you might be confused, right? So this is the property that the sum is multiplicative. In other words, if this happens, then what is the statement? F of, I will use different letter. So alpha beta equals f alpha f beta, right? Because I used these things, I should, if GCD of alpha beta is 1, right? Do you get it? So I'm going the other way. If f is multiplicative, sum is multiplicative. Now going the other way. Sum is multiplicative and f is. How? By what? Mobius inversion formula. So I will continue unless you have a question about the properties of. It's the property, not the proof. And let's do it. So, proof. If GCD of alpha beta is 1, then f alpha times beta equals, by Mobius inversion formula, some divisor dividing alpha times beta, and then I didn't name the sum, so I will say just sum, right? Sum of D, right? So sum didn't have any name, so I attached the name SS of D, where S of D represent the sum, right? Do you get it? So this is the definition part. Then the next part is decomposing it, because alpha and beta are relatively prime. We can decompose this to d alpha, d beta. Do you get it? Alpha beta, d divides alpha beta, then some part should divide alpha, some part divide beta, but they do not have common factor, right? Less than, greater than 1, right? They don't have common factor greater than 1. Because if they have common factor greater than 1, then the GCD cannot be 1, right? So they are separate. Do you get it? They are separate. Because of this reason, we can rewrite it. D alpha divides alpha, d beta divides beta, and then mu of alpha beta divided by d alpha portion, d beta portion, and then S d alpha d beta portion. But now, because mu is multiplicative, S is multiplicative by the condition, we can completely decompose and rewrite. Right? So I will say the step. We can completely decompose these things. Because these are given by the condition or property. U is multiplicative, this is multiplicative, and then we can rearrange. So we can rearrange these things into d alpha dividing alpha, and the alpha portion is collected here. And then beta portion is collected here. And then as you can see, this is called what? This is called, by Mobius inversion formula, f of alpha, right? This is called f of beta. And now I showed that f is multiplicative. So when the sum is multiplicative, the summand is also multiplicative. So unless you have a question, I will cover the last function in this today. Last function, that is very easy function, or some function that you already used. But if you have a question about this proof itself, ask me. No question, right? Then the next function, I will not use the textbook notation, but I will use the general notation people use. The greatest integer function, but generally this is called a floor function. Floor function. So assume that some number is here, and then these ceiling or bottom represent non-integers, then we find the floor of this portion. The floor of this portion is found, right? So I will use the notation like this. X and then floor. Opposite concept is ceiling function. If we use these things without this, then it is called ceiling. So this is floor. And we don't use ceiling, but sometimes people use ceiling. Ceiling is written in this way. And in this text, they didn't define floor or ceiling. They only called the greatest integer function, and then they used this notation, Gauss notation, and then they are equal, generally equal. But I will use floor expression because most people in the society, mathematical society, use this thing. I will show you. If I say 1.5 and then this one, it doesn't know, right? But if I say floor of 1.1, 1.5, then what will be the result? 1, right? Do you get it? You always find the floor of, for instance, this point, this thing, right? Then it is what? This thing, floor function. So this is the reason why I will use general notation instead of specific notation for the book. But in any case, notation isn't very important. Assume that you multiply 1 through n. That means n factorial, right? You multiply 1 through n. Then, how many, for instance, power of 2 can you find? Or power of 3 to the power of something can you find? Generally, how many p to the power of something can you find? This is the question. This is the question. Can you guess? For instance, let's do the counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 in 10 factorial. How many 3's can you find? 1, 2, 3, 4, right? It has 2. How many 2's can you find? 1, 2, 3, 4, 5, 6, 7, 8, right? Total 8. This is the key part. In other words, give me P. Give me P. For n factorial, give me P. Then, can you find the power? That is the question. How can you systematically find it? Then I will answer first and then prove later. If you have enough time, I will prove it today. But if you don't have enough time, then I will prove it later. For instance, 2. So you are handling n factorial, but you don't use this factorial portion, just n portion, just 10, not 10 factorial. If you use 10 factorial, it's a disaster. And then assume that you are using 2, I will do this. And then 2 squared, and then 2 cubed, and then, so first power, second power, third power, fourth power, fifth power, and add everything like this. But once it reaches a certain position, the numerator will be smaller than the denominator. Then the floor of some number that has a bigger denominator is automatically what? 0. So we don't have to worry about the convergence, right? This converges, right? Because the tail portion will go to 0 in the end. Then what is it? What is the floor of 10 over 2? 5. What is the floor of 10 over 4? 2. What is the floor of 10 over 8? Then it is 8. You got this 8 by counting it. I got 8 by systematic approach. If you doubt it, I will ask you to count the next thing. So in 100 factorial, how many 7s can you find? In 100 factorial, how many 7s can you count? And some of you may already begin, but on the exam, I may ask you 10,000 over 17, right? Or 17 power, right? So how many 7s can you count? In other words, if we decompose it, for instance, 2 to the power of something, 3 to the power of something, 5 to the power of, so prime powers, right? And then 7 to the power of something. So this is my question. This is my question. 7 to the power of something should be found. So can you really count? No. But do not write factorial here. It's a disaster, as I mentioned. You should avoid writing factorial, but just write n. But already, as you can see, 7 cubed exceed 100. So we don't need this term at all, right? The following term from this position is all 0, right? The only thing that you need to worry is this thing. 100 divided 7 is 1, and then about 34, right? And then this thing divided by this thing is about 2 point something. So there are total 16, right? 7s. So no matter what factorial is given, you can always determine the power. So to test it, I will ask this thing. In 1,000, how many 29th power exists? Please find this power. How many 29th power exist? Sorry. You are right, 1,000 factorial. Doesn't look nice. I'll rewrite it. So did you already find the result? What is it? What is it? $35, right? 34 upstairs, 31. 35, right? 35, 29. Do you get it? Then the next question is the proof. Once you know, you want to know the proof. You want to know the reason. So let's do it. This might be the end of the story today. So let's do it. So the only thing is just counting. One, I cannot write down the numbers very small, so I will just use dots, right? 4, 5, 6, 7, 8, 9, 10, 11, and then all the way up to n, right? So let's assume that we are counting 3. Then 3 is counted here. And then 6. 6 is 2 times 3, right? 2 times 3, 9. 3 times 3. Do you see the difference? When it doesn't have 3 factor, then I wrote just 2 times 3, right? It doesn't have one repeating 3 factor. I just wrote 2 and then 3. But when it had a repeating factor, I stacked it. Then next number is 4 times 3, 5 times 3, and then 6 times 3, right? Then 2 times 3 times 3. So in this way, we can rewrite it, and then once it reaches 29, 3 times 3 times 3. Do you get it? So in this sense, all the way up to this point, how many 3s can you get if you sum these things? N over 3, right? E number is N over 3. Do you get it? N over 3. E number is N over 3, right? If after each 3, we get 3. So N over 3, we get in this level. In this level, when we reach this thing, then it is 9, and then 9 times 2, 9 times 3, and so on. So when we reach this level, then first level has N over 3, second layer has N over 3 squared, and the third layer has N over 3 cubed, right? So this is the reason why we get these many N's, right? So this is the proof. If I rearrange, then I write it, this is the proof. So we count this thing in this fashion, right? We count it in the first layer, and then when 3 is repeated, we count it, but the interval that this happens is after each 3, right? What about the interval of this happening? Interval 9, right? What about the interval here? 27. 81, right? So this is the reason I can count. So this is the end of the story, and let's stop. I don't want to fry your brains. So let's stop.